how long would it take us to go to Mars? That single question is powerful enough to spark curiosity in scientists, writers, filmmakers, and everyday dreamers alike, because the answer is not simple, not fixed, and not something you can determine with just a ruler and a stopwatch. Mars is close enough to be our most realistic next home, yet distant enough that getting there pushes our technology, biology, and imagination to their limits. The distance changes constantly. The travel path is never straight. The spacecraft involved must obey the laws of orbital mechanics, and the time required depends on everything from planetary alignment to propulsion power. So, watch this video till the end and subscribe to the channel. Let's begin. To understand how long a human journey to Mars might take, we first need to understand how far away Mars actually is. And here's where the first complication strikes. There is no single number. Mars and Earth both orbit the Sun in elliptical, slightly stretched out paths, like two runners sharing a track but moving at different speeds and distances from the center. Sometimes those runners end up relatively close together. Other times they are on opposite ends of the track, with the Sun sitting between them like a cosmic referee. When Earth and Mars align on the same side of the Sun, a position known as opposition, the distance between them can shrink to about 54.6 million kilometers, 33.9 million miles. But when Mars swings behind the Sun, entering what we call conjunction, the gap can widen to over 400 million kilometers, 249 million miles. That's the difference between a long road trip and circling the Earth more than 1,000 times. Because the planets are always moving, their separation is constantly changing, minute by minute, second by second. That's why giving an exact distance is like trying to state the exact distance between two kids running around a football field without pausing. Even the famous average distance to Mars, often quoted around 225 million kilometers, 140 million miles, is only useful as a rough midpoint, not a constant value you can build a mission around. Engineers planning a Mars journey don't use a single number. They use constantly updating orbital calculations and predictive models that forecast where each planet will be months or even years into the future. Distance to Mars is not a static measurement, it's a moving target across space and time. And this constant motion is exactly why traveling to Mars is not as simple as burning engines and pointing a spacecraft straight ahead. Orbital mechanics is the reason space travel feels less like shooting an arrow and more like throwing a ball that must curve perfectly through space. If Earth and Mars were parked motionless in the void, we could simply aim at Mars and hit the gas. But the planets are constantly moving around the Sun, each at different speeds, each on its own elliptical track, meaning Mars won't be where we see it by the time a spacecraft arrives. Imagine trying to jump onto a moving carousel from another carousel that's also spinning. To land at the right spot, you don't aim where the horse is, you aim where it will be. A spacecraft doing the same thing must follow a curved path known as a transfer orbit, using the gravity of the Sun as both guide and obstacle. This is where orbital mechanics becomes more like choreography than travel. The spacecraft is essentially falling around the Sun, gliding along a path known as a Hohmann transfer orbit. It's an energy-efficient trajectory. You boost your speed to escape Earth's gravity, then allow the Sun's gravitational field to pull you along a precise elliptical arc toward Mars orbit. But here's the catch. You don't aim directly at Mars. Instead, you aim for the spot where Mars will arrive months later. A tiny miscalculation early in the journey could result in missing the planet by millions of kilometers. This is why mission planning involves complex simulations of planetary motion, engine burns, mass distribution, solar radiation pressure, and even micrometeoroid hazards. Another key point is that space doesn't have brakes. Once you're moving, you stay moving. If you go too fast, you might shoot past Mars entirely and never stop. If you go too slow, you may reach Mars's orbit long after the planet has moved on. Engineers must balance speed and precision, timing their launch so the spacecraft meets Mars at the perfect intersection in space, like two cars merging into a lane without ever touching the brakes. The path curves, the timing matters, and travel time depends on much more than just raw distance. Orbital mechanics ensures that getting to Mars is a dance with gravity, motion, and momentum, rather than a straight flight path across a cosmic highway. Chapter complete. Launch windows are the natural consequence of these orbital mechanics, and they dictate when we can go. Because Earth and Mars travel around the Sun like two gears turning at different speeds, there are only certain moments when they line up favorably for travel. A launch window is like a brief opening in a revolving door. Miss it, and you either wait for the next one or spend much more energy getting through a partially open gap. Generally, these prime opportunities come approximately every 26 months, when Mars and Earth align in a configuration that allows a spacecraft to take a relatively efficient Hohmann transfer orbit. During this window, the planets are positioned such that the spacecraft can depart Earth, follow an elliptical path, and intersect Mars' orbit at the right moment with a manageable amount of fuel. But even within that window, timing can be narrowed to just a few weeks, depending on the mission's goals. If you launch too early or too late, the spacecraft might arrive when Mars is slightly off position, requiring extra course corrections that burn fuel. And in spaceflight, fuel is everything. Scientists analyze not only orbital geometry, but also solar activity, spacecraft mass, engine efficiency, and mission destination, orbit, landing site, or return flight. Launch windows are precious. Miss one, and your spacecraft may have to wait years in storage or sit on the launch pad until the planets align again. These windows aren't suggestions. They are rules carved by the mechanics of the solar system. And this predictable yet unforgiving timing shapes every Mars mission humanity has ever attempted. Our future crewed missions will depend on them too, because even with advanced propulsion, saving fuel means saving money, mission mass, and risk. That cosmic gate only opens every couple of years, reminding us that reaching Mars isn't just a matter of engineering. It's about patience, precision, and working with the rhythm of the solar system, rather than against it. Launch windows are one of the most important, yet often overlooked, factors when determining how long it takes to reach Mars. They're not just calendar suggestions or scheduling conveniences. They're the cosmic golden gates that either allow a spacecraft to travel efficiently or make the entire mission nearly impossible. Earth and Mars are constantly moving around the Sun at different speeds. Earth completes an orbit in about 365 days, while Mars takes roughly 687 days. Because of this, they align favorably only every 26 months, creating a narrow period where a spacecraft can take advantage of the shortest and most energy-efficient path known as the Hohmann transfer orbit. If you launch outside this window, reaching Mars becomes exponentially harder, requiring significantly more fuel and time, and sometimes making the destination unreachable with current technology. Think of it like waiting for two moving train cars to line up so you can jump between them. You can't leap whenever you feel like it. You have to time your jump so that the other train passes beside you at the right moment. A Mars mission works the same way. We aren't chasing Mars across the solar system. We're predicting where it will be months in the future and launching at just the right second, so both spacecraft and planet arrive at the same intersection of space at the same time. Engineers calculate launch windows using massive orbital simulations that factor in gravitational pull, planetary velocity, spacecraft mass, sunlight, potential dust storms, solar radiation predictions, and even the angle at which the spacecraft will enter Mars' atmosphere. The simplest version you sometimes hear, launch every 26 months, is only the surface. The real launch window is a carefully calculated slice of time, sometimes narrowed down to just a few weeks, where the arc of the spacecraft's journey will meet Mars's orbit perfectly, like two puzzle pieces snapping into place. Even within an available window, not all trajectories are equal. Some launch days lead to a quick, fuel-efficient journey. Others may get you to Mars but require weeks or months of extra travel time because they follow a less optimal curve around the Sun. Mission planners must decide what matters most: speed or fuel efficiency. If the window is missed entirely, the spacecraft can't simply turn and go anyway. Doing so would require engines powerful enough to push against the geometry of the solar system itself, something far beyond our current propulsion capabilities. This is why missions like Perseverance, Curiosity, and every orbiter before them all launch during specific windows and with carefully planned timing. Billions of dollars, years of preparation, thousands of people, all depending on a planetary alignment that nobody can change or delay. The solar system sets the schedule, and humanity must follow it. Launch windows shape more than travel time. They shape mission timelines, budgets, astronaut schedules, and technology development, when multiple nations race to meet the same alignment window. Every future crewed mission to Mars will be built around these windows just as strictly. They are the heartbeat of interplanetary travel, opening and closing with cosmic precision. And when the next window arrives, humanity must be ready, because space waits for no one, and Mars will not stop moving for us. When planning a journey to Mars, distance isn't just a number. It's a fluctuating, dynamic variable that changes everything from fuel consumption to travel time to the psychological strain astronauts must endure. The shortest path, the longest detour, and the typical in-between all shape how we design missions. When Earth and Mars are at opposition, meaning Earth sits directly between Mars and the Sun, the planets can come as close as 54.6 million kilometers. That's the cosmic sweet spot, the moment mission planners dream of. Launch during a favorable opposition, and you're looking at the most efficient trajectory, the least fuel use, and the fastest possible interplanetary transit using current propulsion technologies. This is why so many robotic missions have lifted off during these periods. But even at their closest, Mars is never conveniently parked in place. A spacecraft still must follow a curved Hohmann transfer arc, arriving months later, hopefully exactly where Mars will be rather than where it is. On the opposite side of the spectrum is conjunction, the worst-case scenario for distance, when Mars sits behind the Sun from Earth's point of view. During this alignment, the two planets can be separated by more than 400 million kilometers, with the Sun acting like a giant wall of radiation and communication interference between them. Not only is the physical distance massive, but no one would dare launch a crew through a region where radio signals weaken, solar storms intensify, and a straight path would mean slingshotting dangerously close to the Sun's gravity well. This is why Mars missions aren't scheduled during conjunction. It's simply too far, too risky, and too energy-consuming. Instead, spacecraft orbiting Mars often switch into safe communication modes during conjunction because even maintaining contact becomes a challenge. If we can't reliably talk to robotic probes, sending astronauts at that distance would be a gamble no agency is currently willing to take. Somewhere between those two extremes lies what most people refer to as the average distance between Earth and Mars, roughly 225 million kilometers. But average is a misleading comfort word. Space doesn't give us averages to work with. It gives us constantly changing orbital geometry. One launch window might place Mars at 70 million kilometers away, the next at 100 million, the next at 120 million, depending on both planets' positions along their elliptical paths. Each shift changes how much fuel we need, how long the spacecraft must haul supplies, how much shielding is required for radiation exposure, and how much wear and tear the crew will endure. Launch during a favorable window near opposition, and travel might be as short as 6 to 8 months. Launch when Mars is farther along its orbit, even if still technically reachable. And that same journey can lengthen dramatically, stretching toward a year or more. Mission planners begin with distance calculations long before rockets are built. These values dictate how heavy the spacecraft can be, how much cargo it must carry, how strong engines must burn, and how much margin they need for mid-course corrections. A few million kilometers difference might not sound like much on the cosmic scale, but in mission design, it can mean the difference between a high-risk gamble and a smooth glide across interplanetary space. Distance isn't just geography, it is strategy. It shapes everything. And because Earth and Mars are never still, humanity's path to the red planet is always shifting, changing, and challenging us to hit a moving target inside a vast and unforgiving arena. Robotic missions give us the clearest real-world evidence of how long it takes to reach Mars. Not estimated, not theoretical, but measured through decades of exploration. Each probe, orbiter, and rover launched toward the red planet has been a data point in humanity's growing map of interplanetary travel. When we look back, patterns begin to emerge. Most successful missions fall roughly into the 6 to 9 month transit window, though the exact time always depends on launch date, rocket configuration, and the trajectory chosen. One of the earliest examples, Mariner 4 launched in 1964, took about 228 days to cover the distance and return the first close-up images of another planet. Viking 1, one of NASA's earliest landers, made the trip in 304 days, arriving in 1976 with the goal of searching for life-related chemistry. The Mars Global Surveyor orbiter took around 308 days, proving that even similar launch windows and similar technology could yield slightly different travel times depending on mass, speed, and path. Fast forward to more modern missions and the pattern holds. NASA's Curiosity rover, launched in 2011 aboard the powerful Atlas V rocket, reached Mars in 253 days, nearly 8.5 months. Perseverance, another rover in the same Mars Science Laboratory family, arrived in 2021 after approximately 203 days, just under 7 months. ESA's ExoMars Trace gas orbiter required about 230 days, while India's Mars Orbiter mission, a milestone for the ISRO program, spent about 298 days in transit, demonstrating that slower or more fuel-efficient trajectories can extend travel time significantly. Even the rapid Mariner 6 and 7 missions, often cited among the faster transfers, still took around 5.5 months, proving that shaving time off the trip is possible, but not dramatically so, with chemical propulsion. None of these robotic explorers sprinted to Mars. They coasted, curved, and carefully aligned themselves across millions of kilometers, following the gravitational geometry that orbital mechanics permits. What's striking is how tight the travel time range has remained across 5 decades of missions. Despite enormous advances in computing power, navigation accuracy, rocket design, and spacecraft engineering, robotic journeys tend to cluster within a consistent time window, This is not a failure of technology, it's a reflection of physics. Launch during a good alignment and you glide efficiently. Launch under different conditions and you might require additional burns, course corrections, or trade fuel efficiency for shorter duration. Even spacecraft with advanced ion propulsion, like NASA's Dawn mission, couldn't reach Mars faster because they were never designed for brute speed. These engines excel in long-duration thrust, not quick interplanetary jumps. Most Mars-bound probes rely on conventional rockets to get off Earth, but once they're moving, they conserve fuel, relying on momentum and gravity to carry them translunar, transsolar, and finally interplanetary. These robotic missions are our rehearsal. Every transit time teaches us something about deep space navigation, radiation exposure duration, trajectory optimization, and how equipment performs after months in cold vacuum. They also establish the psychological expectation we bring to future crewed missions. Not days, not weeks, but months, floating between worlds. And while future propulsion systems may shorten this window dramatically, our robotic explorers remind us where we stand today. 6 to 9 months remains the current standard, long, demanding, but achievable. And every rover that touches Martian soil brings us one step closer to a time when humans will make that same crossing. If robotic missions have shown us the travel time range we currently operate within, propulsion technology explains why those missions take as long as they do, and how we might one day shorten the journey. Not all engines push spacecraft the same way, and each propulsion method shapes the balance between speed, fuel efficiency, and mission capability. Right now, most Mars missions rely on chemical propulsion, the same broad category used to launch Apollo astronauts to the Moon and satellites into orbit today. These engines burn chemical fuel, usually liquid hydrogen and oxygen or kerosene-based variants, producing massive thrust in short explosive bursts. Chemical propulsion is powerful enough to lift rockets off Earth and accelerate spacecraft into interplanetary trajectory quickly. But here's the limitation. Once in space, it's inefficient for sustained acceleration. The fuel required to keep thrusting for months would weigh far more than any rocket could reasonably lift. As a result, chemical propulsion gets you moving fast, then your spacecraft coasts like a thrown stone, guided not by continuous power, but by momentum and orbital mechanics. To travel faster without carrying mountains of fuel, engineers have looked to more efficient alternatives. One promising option is ionic propulsion, also known as ion drive technology. These engines don't rely on fiery combustion. Instead, they use electricity, often generated by solar panels, to accelerate charged particles like xenon ions out of the thruster at incredible speeds. The thrust is minuscule, often compared to the weight of a sheet of paper resting on your hand, but it never stops. Over months, that constant push adds up, allowing ion-powered spacecraft to gradually reach speeds chemical rockets could never sustain. NASA's Dawn spacecraft demonstrated this beautifully, spiraling through the asteroid belt on engines that sipped fuel rather than gulped it. Ion propulsion could shorten Mars travel time if we could use it for initial departure and not just deep space cruising. But current ion engines can't produce the raw thrust needed to escape Earth's gravity well. They excel in space, not on launch pads. Then enters a propulsion category with far more power on the table: nuclear propulsion. There are two primary branches: nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP, each with distinct advantages. In nuclear thermal propulsion, a reactor superheats hydrogen to extreme temperatures and expels it through a nozzle, producing thrust roughly twice as efficient as chemical engines. That increased efficiency means shorter transit times, potentially cutting a Mars trip from 7 months to 3 or 4. NEP takes a different approach. Instead of heating propellant directly, the reactor generates electricity, powering ion-like thrusters for long-duration acceleration. NEP systems could enable even faster cruising speeds, although they are heavier, more complex, and require robust shielding to protect astronauts from reactor radiation. Both nuclear propulsion systems are strong contenders for future crewed missions, and NASA, along with DARPA, are actively testing concept reactors as part of the Draco program. Beyond nuclear systems lie technologies still forming on the horizon, propulsion concepts that might one day shrink Mars travel from months to weeks. Solar sails harness sunlight like wind in a cosmic ocean, gradually accelerating spacecraft without using fuel at all. The Japanese Icaros mission proved this system works, though scaling it up for human transport remains a massive engineering challenge. Plasma-based propulsion, such as VASIMR, Variable Specific Impulse Magnetoplasma Rocket, uses electromagnetic fields to heat and accelerate plasma to produce thrust. Its creators claim it could reduce Mars travel time to 39 days with sufficient onboard power, though that power requirement is enormous and currently unrealistic for crewed missions. And on the far edge of speculation lie fusion drives, antimatter engines, and other propulsion systems that exist more in theoretical physics labs than engineering workshops. Yet their potential is staggering. Fusion engines could provide continuous, high-efficiency thrust, slashing travel time dramatically. Antimatter propulsion, if ever harnessed, could convert mass to energy with 100% efficiency, unlocking velocities we've barely imagined. Propulsion is the heartbeat of interplanetary travel, not just what gets us there, but how fast, how safely, and how sustainably. Chemical engines brought us to where we are today. Ion propulsion charts the path of endurance. Nuclear power promises speed, and future breakthroughs could redefine the very scale of space travel. The history of spaceflight tells us that propulsion evolves the same way exploration always has, step by step until one day everything changes at once. And as we look beyond propulsion itself, the next question becomes clear. What speeds can we actually reach right now, with real rockets and existing technology? That answer is where our journey continues next. Current spacecraft speeds give us the clearest grounding in reality, the hard limits of what today's technology can accomplish without theorizing about future breakthroughs. When rockets leave Earth, they must first reach escape velocity, approximately 11.2 kilometers per second, just to break free from gravity's grip. That's already more than 40,000 kilometers per hour, faster than anything we experience in daily life. Yet it's only the beginning. Once a spacecraft enters interplanetary transfer, its velocity relative to the Sun, called heliocentric velocity, becomes the important measure. Most Mars-bound spacecraft cruise between 20,000 and 30,000 kilometers per hour, an incredible pace that still translates to months of travel because space is unimaginably vast. Even traveling at 100 kilometers per second, it would still take days to cross the solar system's inner region. With current mission profiles, propulsion burns happen mainly at departure, with occasional mid-course adjustments, then months of coasting like a stone skipping across a cosmic pond. Take NASA's New Horizons, often cited as one of the fastest human-made objects ever launched. It left Earth at about 58,536 kilometers per hour, breaking speed records. Yet even at that speed, it would still need several months to reach Mars if redirected. And that's with a trajectory optimized for speed rather than fuel efficiency. Mars missions typically do not chase maximum velocity. They prioritize fuel balance, stability, and safe atmospheric arrival. The Perseverance rover spacecraft traveled at roughly 39,600 kilometers per hour during cruise phase, while Curiosity maintained similar heliocentric ranges, navigating with precision rather than brute speed. The European Space Agency's Rosetta probe reached speeds over 55,000 kilometers per hour, but only after multiple gravity assists. These numbers reveal something important. The speed a spacecraft reaches depends not just on engines, but on trajectory design, mass, planetary alignment, and mid-course propulsion strategy. Even more fascinating is the fact that increasing speed isn't always helpful. If a spacecraft arrives at Mars too fast, it risks slingshotting past the planet or burning up during entry. Engineers must plan a delicate balance, fast enough to minimize travel duration, but slow enough to safely navigate Mars' thin atmosphere or achieve stable orbit. To land, spacecraft rely on atmospheric drag, heat shields, parachutes, and retropropulsion to shed enormous velocity. A crewed vehicle can't simply scream into Mars like a speeding bullet. Stability and safety matter far more than sheer speed. Every meter per second of excess arrival velocity must be counted with fuel or atmospheric braking, adding complexity and danger. A fast trip is impressive on paper, but space travel rewards precision more than power. These real-world speeds show why most missions settle into that familiar 6 to 9 month window. Traveling faster would require exponentially more fuel that must be launched from Earth, increasing mass, cost, structural stress, and ultimately the risk of mission failure. With the rockets we have today, Falcon Heavy, Atlas V, SLS, Ariane 5, Long March 5, we push against the limits of chemical propulsion. They can launch heavy spacecraft beyond Earth's gravity well, but once en route, they rely on momentum and minimal course corrections to conserve propellant. We are fast, but not fast enough to compress interplanetary travel into weeks. For now, speed and practicality intersect at months-long voyages across the void. And yet, speed limits today need not be speed limits tomorrow. As we look beyond current capabilities, the question becomes bolder. If we push performance further with more efficient propulsion, nuclear reactors, or constant thrust drives, how short could the journey become using technology we could build within the coming decades? That is where our next step leads. Estimating realistic Mars travel times using the tools we already have or are close to mastering. Using the technology we have right now, the rockets we can launch today, the engines we have already tested, and the mission profiles we've already flown, we can estimate human travel time to Mars with remarkable confidence. No guesswork, no science fiction, just the physics we've proven through decades of robotic exploration. With conventional chemical propulsion systems like those used for Perseverance, Curiosity, Viking, and countless orbiters, the most realistic travel duration for a crewed mission sits between 6 and 9 months. That's the benchmark window we return to again and again. It's not coincidence. It's the natural result of orbital mechanics, energy costs, fuel capacity, spacecraft mass, and propulsion output. Launch during an optimal window near opposition, follow a Hohmann transfer orbit, and a spacecraft designed today could carry astronauts to Mars in a little over half a year. But that number isn't carved into the cosmos. Change any variable, and the time stretches or compresses in ways mission planners must consider carefully. Why 6 to 9 months? Because that is where physics and practicality intersect. Chemical rockets provide high thrust at launch, enough to lift heavy payloads off Earth, but they are not. efficient for sustained interplanetary acceleration. After escape velocity is achieved and trans-Mars injection is complete, engines shut down, fuel is conserved, and the spacecraft coasts through space with occasional trajectory correction burns. It's similar to pushing a boat away from a dock. A strong initial shove sets the course, but you don't keep paddling the entire way. You drift, adjusting only when necessary. A faster journey would require continuous thrust, burning more fuel along the way, or relying on propulsion methods that aren't yet human-rated or powerful enough for initial Earth departure. This is why faster spacecraft remain theoretical for human crews, despite robotic missions occasionally demonstrating more ambitious velocity profiles. However, even within today's achievable window, travel duration varies subtly depending on launch conditions. If Mars is farther along its orbit at departure, the spacecraft must travel a longer arc, adding weeks or even months to the journey. If the mission prioritizes cargo over speed, travel may be slower but more fuel efficient. Some mission planners even consider pre-deploying supplies to Mars months or years earlier using slower, cheaper trajectories, allowing the crewed portion of the mission to travel lighter and faster. But for the crewed flight itself, the vessel carrying life support, radiation shielding, landing equipment, food, water, and habitats, shaving travel time becomes more difficult. Every kilogram of mass matters. More speed demands more fuel. More fuel increases mass. More mass requires more thrust. More thrust requires more fuel, a cycle that spirals in on itself. Even the most powerful rockets available today, NASA's Space Launch System, SLS, SpaceX's Falcon Heavy, and soon Starship when fully operational, still operate inside this 6 to 9 month envelope. A mission using conventional propulsion might reach Mars in closer to 6 months under optimal alignment, possibly 7 to 9 months under less ideal conditions, and 10 plus months if using low energy, low thrust transfers to conserve propellant. Over time, astronauts could spend nearly as much duration in transit as they will on the Martian surface. And that matters. Because surviving the journey isn't only about engine power. It's about radiation exposure, psychological endurance, microgravity health risks, consumable storage, and system reliability. A slower trip gives more time for failures to occur, but a faster one increases energy demands and risk. That's the trade-off engineering keeps coming back to. Speed versus sustainability. We also shouldn't ignore mission architecture. Some concepts propose splitting missions into 2 launches, one with a cargo lander sent ahead on a slower trajectory, one with a crewed vehicle launched later on a faster route. Others involve staging fuel depots in lunar orbit or using in-space assembly and refueling before departure. Starship, if fully developed, aims to refuel in orbit, enabling more aggressive outbound velocity and potentially trimming travel time. But even with such innovations, we're likely still looking at several months, not several weeks, for the foreseeable future. The barrier isn't imagination, it's propulsion efficiency, spacecraft mass limits, and biological constraints. So, with everything we can build today, the answer to our core question stands clearly. At present, humans traveling to Mars would spend roughly half a year, possibly a bit more, en route between worlds. Long enough to watch Earth shrink into a star-like speck. Long enough to feel completely unmoored from home. Long enough for the journey itself to become a psychological expedition as much as a physical one. But could we do it faster? Could we cut that duration in half, or even quarter it, with near-future propulsion systems that are already on the drawing board? Yes. And exploring those possibilities takes us into the next chapter, where speed is no longer limited by today's engines, but expanded by tomorrow's. While current technology gives us 6 to 9 months of travel time, faster propulsion concepts are actively being developed, some in advanced testing, others still hovering between engineering and future reality. If chemical rockets are sprint starters and ion engines are marathon runners, then next-generation propulsion aims to be a high-efficiency bullet train across the solar system. The most mature and realistic contender for reducing Mars travel time is nuclear thermal propulsion, NTP. Instead of burning chemical fuel, an NTP engine uses a compact nuclear reactor to superheat liquid hydrogen to extreme temperatures and expel it through a nozzle, doubling the efficiency of the best chemical systems we have. That means more thrust per unit of fuel, faster acceleration, and significantly shorter transit times. NASA and DARPA are already developing prototype reactors through the Draco program, aiming for space-based tests soon. If NTP performs as expected, travel time to Mars could drop to 90 to 120 days, roughly 3 to 4 months. That alone would be transformative for human missions, reducing radiation exposure, psychological strain, and life support requirements by nearly half. Beyond NTP lies nuclear electric propulsion, NEP, essentially combining the sustained efficiency of ion drives with the raw power of a nuclear generator. Instead of heating hydrogen directly, NEP uses a reactor to produce electricity that powers high-efficiency thrusters. NEP engines can run continuously for months, gradually accelerating to much higher velocities than chemical propulsion can ever achieve. Missions using NEP could theoretically reach Mars in 45 to 90 days, depending on reactor output, spacecraft mass, and mission profile. But there are obstacles. Reactors are heavy, heat dissipation is challenging, and shielding is essential to protect astronauts from radiation. Even so, NEP sits firmly in the realm of near future, not fantasy, a technology we could see powering deep space missions within the next decades. Another concept relies not on fuel tanks, but on the sun itself, solar sails. These vast reflective sheets capture momentum from photons, particles of light, and use it as propulsion. Each photon exerts a tiny push, like wind on a sailboat, but that push never stops. Over weeks and months, a solar sail spacecraft could reach tremendous speeds without burning a gram of propellant. Japan's Ikaros mission proved the technology works, and the Planetary Society's light sail tests have demonstrated continuous photon-driven acceleration. The challenge isn't propulsion, it's scale. A human-rated sail capable of reaching Mars quickly would need to be enormous, possibly spanning kilometers. Solar sails are elegant and efficient, but still impractical for transporting large crews, heavy radiation shielding, and cargo. Still, the long-term promise is enormous. For lightweight probes, solar sails could eventually deliver travel times far shorter than conventional rockets. Then, there are propulsion systems that sit closer to science fiction, yet remain scientifically sound in principle. VASI-MR plasma engines, currently in development, heat propellant into plasma and accelerate it using electromagnetic fields. Their creators claim that, with enough input power, likely from a nuclear reactor, a VASIMR-powered spacecraft could reach Mars in 39 days. The hurdle is energy supply. Powering a VASI-MR engine at that level would require megawatts of electricity, far more than current space-rated reactors can provide. But if energy production in space improves, plasma propulsion could reshape interplanetary travel entirely, farther out, still beyond practicality, but not beyond physics, lie fusion drives and antimatter propulsion. Fusion engines would replicate the process that powers stars, releasing vast energy from light atomic nuclei merging. In theory, a fusion-powered spacecraft could accelerate continuously, cutting travel times to weeks or even days. Antimatter would go further still, converting matter to energy with 100% efficiency. A few grams could power a spacecraft farther than tons of chemical fuel. These concepts remain experimental and massively expensive, but history shows us that radical ideas tend to become real when enough time, money, and scientific progress accumulate. All of these faster propulsion systems share one promise: less time in deep space, less radiation, less bone loss and muscle atrophy, less psychological isolation, more mass available for supplies instead of fuel. The faster we go, the safer astronauts will be, but only once the engineering is ready. Speed is not just a luxury in spaceflight, it's survival. If nuclear thermal propulsion matures, if plasma drives scale, if fusion becomes controllable, Mars could become not a distant destination, but a reachable nearby world. And once we explore faster ways to get there, the next question grows even more ambitious. What ultimate propulsion breakthroughs might collapse that 3-month or 2-month travel time even further? That leads us naturally into the next chapter, envisioning propulsion revolutions that could change Mars travel forever. Future propulsion breakthroughs carry the potential to reduce Mars travel from months into mere weeks, or even days, transforming interplanetary travel from a high-risk expedition into routine transportation. These aren't the engines we can build today, but they are rooted in theoretical science and engineering that many believe could eventually become reality. The most promising candidate is fusion propulsion, a concept that mirrors the power source of stars. Instead of burning chemical propellants, a fusion engine would fuse light atomic nuclei like hydrogen isotopes, releasing staggering amounts of energy. A fusion-powered spacecraft could accelerate continuously instead of coasting, gaining speed over time rather than losing it. In this scenario, a crewed journey to Mars might take 30 to 60 days, and possibly even less with optimized trajectories. Several research efforts, including the Princeton Plasma Physics Laboratory's fusion propulsion concepts and private sector designs like Helion and Pulsar Fusion, are exploring compact fusion reactors that could one day serve as space engines. Right now, though, sustained fusion power remains one of the hardest technological achievements ever attempted. Clean, controlled fusion has still never been sustained for more energy output than input. But if that barrier falls, space travel changes forever. Beyond fusion lies a propulsion method almost frightening in capability: antimatter engines. Antimatter annihilates upon contact with normal matter, releasing pure energy via Einstein's famous equation E equals mc squared. No rocket concept known to humanity has a higher theoretical energy density. A spacecraft powered by antimatter wouldn't just travel faster, it could achieve a significant fraction of the speed of light, making Mars a short-distance commute by comparison. At such velocities, Mars could be reached in days or even hours, depending on mission profile and radiation management. The limiting factor is production. Creating antimatter requires enormous energy. Our current global output in a year could barely generate micrograms of antiprotons. Storing antimatter is an equal challenge. It cannot touch physical containment walls, or it annihilates instantly. Thus, we would need magnetic or plasma field traps capable of holding charged particles indefinitely, without quenching or failure. This is engineering at the edge of imagination, yet not impossible. particle physics labs have trapped individual antimatter atoms already. Extrapolating that to kilograms is a leap of astronomical scale, but not a violation of physics. A third speculative technology, often discussed quietly among propulsion researchers, is beamed propulsion, where spacecraft carry minimal onboard fuel. Instead, massive ground-based or orbital laser arrays would accelerate reflective sails or plasma engines across space. This removes the fuel mass penalty entirely, the single greatest barrier to speed. In such a system, a Mars-bound craft could be accelerated to extraordinary velocity early in transit, cutting travel time dramatically. Another far-future idea is warp field propulsion, inspired by general relativity. While a warp drive would not move a spacecraft faster than light in the traditional sense, it could manipulate space-time itself, contracting space in front of the vessel and expanding it behind, allowing effective superluminal travel without breaking physical laws. NASA has already funded preliminary theoretical studies on Alcubierre-style warp geometries, exploring whether microcurvature effects can be generated in a laboratory setting. Results so far are inconclusive, but intriguing enough that research has not stopped. Even if warp travel never becomes achievable, there are other exotic possibilities. Quantum vacuum drives, antimatter-catalyzed nuclear propulsion, photonic thrust arrays, or gravitational sailors that surf the curvature of space-time itself. Every one of these concepts, if developed even partially, could reduce Mars travel drastically. What today takes half a year could someday become a trip measured the way we measure transoceanic voyages. Long, but familiar. Push further, and Mars becomes commuter distance. Weeks. Push further still, and Mars could be closer than a flight from New York to Sydney. The kind of leap that changes not only mission planning, but human psychology and civilization itself. The Red Planet would stop being a far-off destination of hardship and isolation, and become a second continent, another reachable piece of home. But faster propulsion is only one side of the story. Cutting the travel time helps immensely, but even with ideal propulsion, long-duration missions come with challenges far beyond engines and fuel efficiency. Space is not empty, it is hostile. Radiation can tear through DNA. Weightlessness erodes bone and muscle. Isolation strains the mind. Supplies must last not days, but months. So even if we could reach Mars in 60 days, or 30, or 10, the next challenge is keeping humans safe and functional along the way. Which brings us to the next chapter, the human cost of deep space travel, and the biological obstacles standing between us and a safe arrival on Mars. The dream of reaching Mars often focuses on rockets and propulsion, but the true challenge lies in what happens after launch. When astronauts are sealed inside a steel habitat for months, separated from Earth by millions of kilometers, reliant on systems that must never fail. Long-duration space travel is not just a technological mission. It is a biological, psychological, and logistical trial, unlike anything humans have ever endured. A Mars transit pushes the human body into an environment where evolution offers no instruction manual. Every day in microgravity chips away at muscle mass and bone density. Astronauts aboard the ISS lose up to 1 to 2% of bone density per month without intense exercise. Their hearts reshape, fluids shift toward the head, and vision often degrades. A condition called spaceflight-associated neuroocular syndrome, SANS. Over 6 to 9 months, those effects accumulate. Even with daily training, medication, and monitoring, the human body struggles to adapt. then struggles again to readapt when gravity returns. A crew arriving at Mars after a long transit could be physically weaker when they need to be strongest. Stepping into Mars's gravity, operating heavy equipment, and possibly performing emergency maneuvers. Microgravity harms the body quietly but relentlessly, yet radiation poses a threat that is louder, more final. Outside Earth's magnetic shield, astronauts are bombarded by galactic cosmic rays and solar particle events, high-energy charged particles that slice through DNA like tiny bullets. Over a 6-month journey, radiation exposure could exceed current career dose limits for astronauts. A sudden solar storm could deliver lethal exposure in hours if shielding is inadequate. These aren't theoretical risks. They are measured realities. ISS astronauts remain partially shielded by Earth's magnetosphere, but a Mars crew would be fully exposed for months. Shielding adds weight. Weight adds fuel cost. Fuel cost adds complexity. Every gram of protective material must be justified, calculated, and optimized. The longer the journey, the higher the cumulative dose, making trip duration not just a convenience, but a matter of survival. Then comes the psychological frontier, arguably the most unpredictable variable. Humans are social, sensory-driven beings. We are wired for blue sky, wind, fresh smells, autonomy, novelty, and physical space. A Mars spacecraft offers none of these. It offers recycled air, filtered water, limited privacy, artificial lighting, and a handful of crewmates who cannot leave, cannot escape conflict, and cannot communicate with home in real time. Delay between messages grows as the ship travels farther, 5 minutes, 10 minutes, 20 minutes each way. No phone calls, no live conversations, just delayed text, like messages from another century. On Earth, tension in a room can be resolved by stepping outside. On a Mars ship, stepping outside means death. Cohesion, emotional regulation, and conflict management become mission-critical skills, as vital as piloting, engineering, or medical training. Depression, anxiety, sleep disruption, sensory deprivation, and interpersonal conflict are not side effects. They are expected challenges. Imagine 6 months of confinement inside a habitat no larger than a small apartment. Every sound becomes familiar. Every routine repeats. Every face becomes unavoidable. Small irritations can grow into threats if morale weakens. Mission planners study Antarctic research stations, submarines, and isolation experiments like Mars 500 and HYSEAS, where volunteers simulate long missions to observe psychological strain. Results show consistent patterns. Communication delays lead to frustration, isolation dulls motivation, and monotony erodes emotional resilience. The Mars 500 crew experienced periods of lethargy and decreased efficiency despite ideal conditions. Now, imagine the same scenario with actual danger, actual responsibility, and no possibility of rescue. Logistics form yet another layer of difficulty. Life support systems must operate flawlessly for months. Oxygen generation, carbon dioxide scrubbing, temperature control, water purification, waste recycling. Every system must be redundant, repairable, and failure tolerant. A single malfunction could threaten the entire mission. Water is heavy, food degrades over time, and packaging creates waste. A crew of 4 to 6 astronauts could require several tons of consumables, and every kilogram counts. Hydroponic or algae-based food systems could help, but they require space, power, maintenance, and risk biological contamination. Spacecraft must be stocked like mini ecosystems, balanced, self-sustaining, resilient to interruption. They must withstand micrometeoroid strikes, solar storms, electrical faults, microbial growth, and human error for half a year or more, with no resupply and no repair crew waiting at the next port. Then there's the unknown, the problems we haven't even discovered yet. Long-term immune suppression, altered microbiomes, unexpected hormonal shifts, cognitive fatigue under deep space radiation, psychological effects of seeing Earth shrink into a star, knowing you cannot return quickly. These unknowns are as daunting as the known dangers. The ISS taught us much, but it orbits a safety net. Mars travel tears that safety net away. No rescue mission can reach a distressed crew in time. No spare parts lie in storage a few days away. Astronauts must solve every problem with what they carry or what they can invent, like Apollo 13, but for months instead of days. And yet, humans have always pushed against the edge of survival, crossing oceans in wooden ships, living in polar darkness, diving miles beneath the sea. We adapt, we innovate, we endure. The challenge is enormous, but not insurmountable. Which leads us into the next chapter. A danger even more fundamental than isolation or microgravity. Radiation, the invisible force that will shape spacecraft design, crew protection, and mission duration more than any other variable. Radiation exposure is one of the most formidable obstacles between humanity and Mars. Not glamorous, not cinematic, but deeply fundamental. We are used to thinking of space as empty, a silent vacuum. In reality, interplanetary space is more like an invisible battlefield filled with high-energy particles that stream through the solar system at nearly the speed of light. On Earth, we are protected by the magnetic field and thick atmosphere, a planetary force field that shields us from most cosmic radiation. The moment a spacecraft leaves Earth's magnetic cocoon, that protection fades. On a Mars journey, astronauts would face galactic cosmic rays, GCRs, particles born from supernova explosions, light years away, and solar particle events, SPEs, massive bursts of radiation from the sun that can spike unpredictably with almost no warning. Over 6 to 9 months, without strong shielding, cumulative radiation exposure could exceed NASA's lifetime career limits for astronauts. That limit exists for a reason. Sustained radiation can break DNA strands, increase cancer risk, accelerate neurological decline, and damage organs at the cellular level. Radiation isn't like heat or cold. You can't feel it while it's happening. There's no pain, no alarm bell, no warning other than sensor readouts and solar weather forecasts. A single strong solar storm during transit could deliver a lethal dose in hours if shielding were insufficient. On the ISS, astronauts are still partially within Earth's magnetic protection and receive roughly 10 times more radiation than a person on the planet's surface. A Mars crew, unprotected, could receive hundreds of times more, with exposure accumulating every moment the spacecraft moves through interplanetary space. The danger is relentless, clock steady, always increasing. This is why propulsion and travel time are inseparable from radiation risk. The longer the crew is exposed, the greater the danger. Faster propulsion isn't just a matter of convenience. It's a preventative shield made of time itself. A 3-month trip instead of 9 cuts exposure drastically. A 6-week transit could reduce risk even more. Time, in this context, is life support. Shielding becomes a brutal trade-off. The most effective radiation protection involves dense materials like water, polyethylene, or hydrogen-rich composites. Some designs even propose surrounding crew quarters with water or fuel tanks, turning consumables into dual-purpose shielding. but shielding is heavy, and every kilogram added must be launched, accelerated, and transported all the way to Mars. More mass means more fuel, more cost, more structural stress, and often longer travel time. This creates the mission design paradox. We need more shielding to stay safe, but more shielding slows the journey and increases exposure. Engineers must find balance, optimizing materials, thickness, and distribution, like surgeons deciding how much armor a knight can wear before he can no longer move. Another approach relies on storm shelters, small, heavily shielded compartments inside the spacecraft where astronauts could take refuge during major solar events. These shelters must be durable, radiation resistant, and stocked for hours or days of confinement. But they don't solve the long-term GCR problem, which is constant and isotropic, bombarding from all directions. Some propose magnetic shielding, using superconducting coils to generate a mini magnetosphere around the ship. It's elegant and reminiscent of Earth's own protection, but generating a magnetic field large enough to shield a crewed spacecraft would require immense power and cryogenic cooling systems that don't yet exist in space-rated form. There are even more radical possibilities. Pharmaceutical radiation protectants, DNA repair treatments, gene editing for radiation resistance, or biological countermeasures that strengthen cells against damage. But those are future solutions, requiring breakthroughs in medicine and ethics alike. Genetic modifications to make astronauts radiation tolerant raise enormous questions about identity, risk, and the nature of human evolution. Yet, if voyages shorten from months to weeks, many of these biological concerns decrease dramatically. Once again, propulsion dictates biology as much as engineering. Radiation shapes everything: spacecraft structure, life support design, mission duration, trajectory, even where crew will sleep. The need to minimize exposure pushes engineers toward faster propulsion, lighter shielding strategies, hybrid materials, and intelligent spacecraft architecture. It also shapes launch windows. Solar activity follows an 11-year cycle, meaning missions are safer during solar minimum and riskier during maximum. NASA doesn't just plan around planets, it plans around the sun itself. So travel time isn't an abstract curiosity. It's the difference between manageable risk and mission-ending danger. Shielding decisions ripple outward into fuel requirements, payload mass, propulsion choices, and even psychological conditions, because every hour spent in space is another hour exposed. Reducing transit duration may be the single most effective radiation mitigation strategy we have. But radiation is only one weight in the engineer's balancing act. The next factor is just as critical to travel time and mission construction: fuel, mass, and cargo. Getting to Mars isn't just about speed. It's about carrying everything you need to survive the journey and return. When thinking about getting to Mars, it's easy to imagine that we can simply add more fuel and push harder. But in spaceflight, it's never that simple. Every kilogram of fuel adds mass to the spacecraft, and every kilogram of mass requires more fuel to move. A trap that engineers call the tyranny of the rocket equation. This principle lies at the heart of mission planning. To accelerate faster, you need more propellant, but hauling more propellant requires stronger engines and even more propellant to lift that extra weight. It's an exponential loop with brutal limitations. A spacecraft optimized for speed must either sacrifice cargo space, reduce shielding, limit crew size, or adopt a propulsion technology capable of much higher efficiency than chemical rockets. Today's Mars-bound missions strike a delicate compromise. They carry just enough fuel to escape Earth, complete the trans-Mars injection, and perform correction burns along the path. After that, they coast. not because engineers want to coast, but because carrying continuous thrust fuel would make the spacecraft so heavy that launching it becomes astronomically expensive or physically impossible. Cargo is where this balance becomes even more unforgiving. A crewed Mars mission isn't simply sending people, it's sending a self-contained survival ecosystem. Astronauts need water, oxygen, food, medical supplies, scientific equipment, habitats, landing systems, ascent vehicles for return, radiation shielding, spare parts, and repair tools. A minimal, tightly rationed mission still involves tens of tons of supplies. A safer, more comfortable mission would require much more. Add to that the fuel needed for descent and ascent on Mars, where gravity is weaker than Earth's but still strong enough to demand significant propulsion. In many mission architectures, fuel for the return trip must be pre-sent or manufactured on Mars through ISRU, in situ resource utilization. If return fuel has to be carried from Earth, mass skyrockets and feasibility collapses. This is why concepts like using Martian CO2 to produce methane and oxygen propellant, as SpaceX plans with Starship, aren't luxuries. They are necessities. Even water illustrates the complexity. Water is essential for drinking, oxygen generation, and radiation shielding. But it is extremely heavy. 1 liter is 1 kilogram. A 6-month mission for 6 astronauts could require 1,000 liters or more without recycling. Modern spacecraft recycle up to 90% of onboard water, but even that remaining 10% means hundreds of kilograms must be packed or generated. Food is lighter but bulkier. Freeze-dried meals pack densely, but they degrade nutritionally over time and require water to prepare. Fresh food requires gardens. Gardens require volume, lighting, power, automation, nutrients, and risk management. Every system adds mass. Every gram must be justified. This is why engineers explore modular mission profiles. One spacecraft might deliver pre-supplies years earlier via slow, low-energy trajectories. Another transports habitats or return fuel generators. The crewed vehicle launches last, optimized for shorter transit time with minimal cargo weight because supplies are already waiting. This staging reduces risk, reduces mass, and potentially shortens travel duration by enabling lighter spacecraft. But it also adds complexity. Every module must arrive successfully, operate correctly, and survive Martian dust storms, temperature extremes, and radiation exposure until humans arrive. Cargo cannot fail. If one system fails, the crew may die on arrival or be unable to return home. Fuel decisions also shape propulsion. Nuclear thermal propulsion could halve travel time without doubling fuel mass thanks to its efficiency. Ion drives need tiny fuel quantities but enormous electrical power. Solar sails require no propellant but demand massive surface area. Fusion or antimatter propulsion would reduce mass dramatically and shorten travel time, but they remain theoretical. Future missions may combine systems: chemical boost off Earth, nuclear propulsion in space, solar electric crews for cargo, each stage optimized for its environment. Mars missions won't be one rocket, but a fleet working as a synchronized ecosystem. So fuel is not just fuel, it's mission architecture. It determines how fast we can travel, how much cargo we can carry, how safe the crew can be, and whether a return journey is even possible. Every decision is a trade. More speed means less payload. More payload means slower travel. Shorter travel requires advanced propulsion. Advanced propulsion needs power, mass, infrastructure, and reliability. The rocket equation governs everything. But astronauts need more than fuel. They need life, literally. Which leads to the next monumental challenge: food, water, oxygen, and waste management systems that must operate perfectly for half a year or longer in deep space without a supply ship or rescue possibility. How do we sustain humans for months while racing between worlds? Surviving months in deep space is far more complex than surviving in a desert, a submarine, or even on the ISS. A mission to Mars requires not just transportation, it requires a closed-loop living ecosystem capable of keeping humans alive without resupply for half a year or more. Life support systems become the true lifeline of the mission, more essential than engines and more unforgiving than navigation. On Earth, humans can survive only minutes without oxygen, days without water, and weeks without food. A spacecraft must deliver all three continuously, reliably, and with margin to spare. Every breath an astronaut takes releases carbon dioxide. Every sip of water must eventually be reclaimed. Every calorie eaten must come from a finite supply or be grown on board. Nothing can be wasted. Nothing can fail. Let's start with oxygen, the most immediate necessity. The spacecraft must provide breathable air, maintain precise atmospheric composition, and remove CO2 before it reaches toxic levels. On the ISS, oxygen is generated through electrolysis, splitting water into hydrogen and oxygen. This system works, but it's energy-intensive, maintenance-heavy, and not 100% reliable. Mars missions require redundancy, backups, and hardware that can run continuously for months without repair facilities. Oxygen can also be chemically recycled using Sabatier reactors that convert carbon dioxide and hydrogen into methane and water, useful for fuel production as well. Even so, failures are deadly within hours. A Mars-bound crew cannot afford a full system shutdown. Their atmosphere must be managed as carefully as rocket fuel. Next comes water, not just for drinking, but for food preparation, hygiene, and oxygen production. Water is heavy, precious, and endlessly reused. Astronauts aboard ISS drink water purified from urine, sweat, and humidity. More than 90% of water is reclaimed, but that remaining percentage matters enormously during interplanetary travel. A crew of 6 might require 30 to 70 litres per day, even with conservative recycling. Over a 6-month mission, that's 5,000 to 10,000 litres before recycling. Unlivable without advanced reclamation. Water is also radiation shielding and thermal mass. Engineers often design spacecraft with water tanks surrounding crew quarters, doubling as life support and cosmic armor. If those tanks leak or become contaminated, survival probability plummets. Food is deceptively simple on paper and immensely complex in practice. Freeze-dried meals work for weeks or months, but long missions require nutrition retention across extended storage. Vitamins degrade, oils turn rancid, and textures become unappetizing. Eating becomes psychological fuel as much as caloric fuel. A 6 to 9 month cruise demands thousands of meals per astronaut. Growing food on board could reduce cargo weight and improve morale, but hydroponic or aeroponic agriculture needs water, power, nutrients, pollination, and space. Plant growth in microgravity behaves strangely. Roots don't know down. Water forms globules instead of flowing, and bacteria behave unpredictably. Experiments on ISS show promise for lettuce, radishes, wheat, and perhaps small vegetable crops, but scaling to full dietary supply remains a challenge. Yet eventually, for multi-year Mars missions or colonies, food growth is not optional, it's survival. Waste, the least glamorous component, may be the most critical. Waste contains nutrients for crop systems, chemical energy, and water locked in biowaste. A closed-loop mission must recycle urine into drinkable water, repurpose fecal matter into fertilizer, methane, or structural building material, recover trace minerals, and prevent harmful bacterial overgrowth. Human waste cannot simply be stored. Storage means mass, space, contamination risk, and odor. Waste must be transformed into resource streams. A Mars mission is less like a camping trip and more like operating an entire municipal utility system inside a metal cylinder. Life support must also manage temperature control, pressure stability, humidity levels, mold prevention, and air circulation. Without gravity, warm air does not rise, and CO2 can pool in pockets around a sleeping astronaut's face, creating suffocation risks even in a room filled with oxygen. Fans and ventilation systems become life-critical components. Sensors monitor everything: oxygen partial pressure, CO2 concentration, microbial content, ammonia, humidity, trace toxins, mold growth. A malfunctioning sensor is dangerous. A failed scrubber is catastrophic. Redundancy is not luxury. It is oxygen, water, survival. Sustaining life also means sustaining minds. Lighting cycles simulate day and night. Personal space is tiny but vital. Crew must exercise to maintain muscle and bone mass, 2 hours per day on ISS, and exercise equipment is heavy, bulky, and power-consuming. Medical emergencies must be treatable with onboard supplies. Small injuries become serious when infection spreads differently in microgravity. Immune function weakens. Wounds heal slower. Dental issues become mission-threatening. The spacecraft must carry medical diagnostics, surgical tools, medication reserves, and at least one astronaut trained as a doctor. And if illness spreads, there is no quarantine bay besides the room everyone lives in. All of this must work flawlessly for months. No resupply, no rescue, no parts store, no hospital. The spacecraft must be a self-repairing habitat, a farm, a recycling plant, a hospital, an oxygen refinery, and a radiation shelter, all while traveling through vacuum at tens of thousands of kilometers per hour. Life support systems turn astronauts into stewards of an artificial environment more fragile than any biosphere on Earth. Yet even with perfect life support and propulsion breakthroughs, one question remains. How fast should we travel? Faster is not always safer. Faster means more energy, higher risk, shorter margin for correction. Slower means greater radiation exposure and longer life support strain. The next chapter explores this balance, the trade-off between speed, safety, cost, and human endurance. Fast travel to Mars sounds like the ideal scenario: less radiation exposure, fewer psychological strains, fewer consumables, and safer overall for the human body. But in spaceflight, faster does not automatically mean safer. The reality is counterintuitive. Pushing speed often introduces new risks that can outweigh the benefits. Every additional kilometer per second of velocity requires exponentially more fuel, more structural reinforcement, more engine power, and more complex guidance. A spacecraft traveling quickly has less margin for error. A minor misalignment becomes catastrophic at high velocity. Course corrections demand more propellant, and if something goes wrong at high speed, there is less time to react. A fast trip can reduce radiation exposure, yes, but it increases mechanical stress, thermal loads, and navigation difficulty. A mission that shaves 2 or 3 months off transit may require twice the complexity. Fast missions also demand fuel, and fuel demands mass. The rocket equation bites hardest here. To cut travel time in half, a spacecraft might need 4 to 8 times more propellant, depending on trajectory. That extra propellant needs storage tanks, cooling systems, structural supports, all of which increase mass even further. Adding mass slows acceleration, requiring even more fuel. Engineers face a spiral where speed requires mass requires thrust requires fuel, and fuel becomes the bottleneck for everything. A spacecraft optimized for fast transit may have to sacrifice life support redundancy, radiation shielding, scientific payload, or surface equipment. The fastest possible mission may not deliver what astronauts need once they arrive. No point arriving in 60 days if the habitat, supplies, or ascent vehicle had to be left behind. Safety also depends on energy. The energy required to accelerate a spacecraft to high velocity must be dissipated later. Arriving at Mars too fast is as dangerous as launching slowly. The thin Martian atmosphere cannot easily slow a massive spacecraft traveling at extreme speed. Heat shields might burn away, guidance control could fail, and G-forces could exceed survivable thresholds. For robotic missions, this risk is manageable, but for humans, margins must be wide and dependable. A safe trip requires controlled deceleration, staging burns, or aerobraking maneuvers, each consuming fuel or exposing the spacecraft to atmospheric heating. If something goes wrong during approach, a sensor glitch, a valve malfunction, an unexpected dust storm, a slower trajectory may give time to troubleshoot, improvise, and survive. Fast missions also come with financial cost. Fuel production, propulsion development, test infrastructure, radiation shielding, nuclear reactors, everything scales up. A mission designed for 3-month transit could cost multiple times more than a 6 to 9-month mission. Governments and private agencies weigh risk against budget. The safest timeline may not be the fastest. It may be the most economically stable and technically feasible. If travel time is cut to 90 days, but cost rises tenfold, such missions might occur rarely, delaying Mars settlement rather than accelerating it. Sustainable exploration often prioritizes reliability over raw speed. A steady cadence of missions builds infrastructure, experience, and confidence. A Mars program will not be defined by a single fast flight, but by dozens of successful slow or moderate ones. Yet slow missions are dangerous too. Prolonged radiation exposure increases cancer risk, cataracts, organ damage, and cognitive decline. Microgravity weakens muscles and bones, increases kidney stone risk, alters immune function, and impacts vision. The longer the journey, the more life support must carry. More food, more water, more oxygen, more waste processing. The longer the crew is confined, the greater the psychological stress, isolation, monotony, disrupted circadian rhythm, interpersonal tension. A slow mission gives systems time to fail. A water recycler malfunction at month 2 of 6 is solvable. A malfunction during month 6 of 12 may not be. Slow journeys expand vulnerability windows, more time for solar storms, micrometeoroid strikes, equipment fatigue, bacterial growth, and software errors. So mission planners juggle opposing forces. Go too fast, and mechanical risk rises. Go too slow, and biological risk grows. The optimal solution often lies between extremes. A moderate speed mission using nuclear thermal propulsion could shorten transit to 90 to 120 days without introducing the high energy risks of ultra-fast transfers. A mission staged with pre-delivered cargo can lighten the crewed vehicle, reducing mass and speeding travel without. Increasing danger. Hybrid propulsion systems may accelerate early, coast efficiently, then decelerate gradually. Engineers tweak trajectory arcs to trade fuel for safety. The ideal balance is dynamic, not fixed. It shifts as propulsion, life support, shielding, and psychological systems evolve. In future decades, as propulsion improves, the safe, fast trade space will shift. Faster transit may someday be both safer and cheaper, especially with fusion or antimatter technology. But today, engineers design missions like surgeons. Every second of travel justified, every kilogram accounted, every risk weighed. Speed alone is never the mission goal. Arrival is, survival is, return is. Fast is desirable. Safe is essential. The real Mars mission will live between the two. And even when astronauts reach Mars, the journey is only halfway over. The next challenge is time beyond transit. How long they stay on Mars, what they do there, and how long they must wait before the planets align for return. Transit time is only one slice of the mission clock. The total mission lasts years, not months, which leads us into the next chapter: mission duration beyond the flight itself. Getting to Mars is only the opening act. The true mission unfolds after landing. Many people imagine a Mars trip like a long voyage followed by a quick turnaround, but reality writes a different story. Because launch windows depend on planetary alignment, astronauts cannot simply arrive, stretch their legs, and fly home. The planets must realign for a viable return trajectory, just like they had to align for departure. Once a crew reaches Mars, they may have to wait more than a year before Earth and Mars again occupy positions that allow an efficient return transfer. In most mission plans, astronauts don't just spend months traveling. They spend 500 to 600 days living on Mars before heading home. This turns what many imagine as a one-year adventure into a 2.5 to 3-year journey at minimum. It is not a trip, it is an expedition. A typical mission timeline looks something like this: 6 to 9 months outbound, 500 plus days on the surface, 6 to 9 months inbound. Total, approximately 900 to 1,100 days, nearly 3 Earth years. Even a shorter stay option, known as an opposition-class mission, still requires more than 30 days on Mars and would demand greater fuel loads for a quicker return, making the mission far more complex. Most mission architectures favor the longer stay duration, not because astronauts want to stay that long, but because orbital mechanics demand it. Mars missions follow celestial schedules, not human ones. This extended stay transforms every aspect of planning. Habitats must withstand dust storms, radiation spikes, temperature swings from -120 degrees Celsius nights to mild afternoons, and micro-meteorite hazards. Life support systems must shift from months to years of reliability. Supply stocks must either be brought from Earth at immense mass cost or produced on Mars through ISRU. Crews will need oxygen generators, water extraction systems, greenhouses or food production modules, and power sources that function despite dust accumulation on solar panels. Nuclear fission reactors may become standard surface power as they operate regardless of weather. Mars is cold, dry, irradiated, oxidizing, and chemically reactive, but it contains what humans need if we learn to extract it. Psychologically, the Mars surface stay may be as challenging as the trip itself. On the spacecraft, monotony dominates. But Mars introduces isolation with constant danger. Astronauts must conduct research, maintain equipment, repair habitats, cultivate food, monitor weather patterns, and perhaps even build structures for future missions. Every task carries risk: a tear in a spacesuit, a habitat seal failure, a dust-clogged valve, a power system malfunction. Any small failure may escalate into an existential threat. Meanwhile, Earth remains a pale dot in the sky. Communication lags persist at 5 to 22 minutes each way, and real-time conversation is impossible. Crews cannot call home for comfort or help. They can only send delayed messages, as though living decades in the past. The return window adds tension. If systems degrade, if illness emerges, if supplies dwindle too quickly, the crew cannot simply leave early. There is no abort to Earth option. They must wait for planetary alignment. Only when Earth swings into the right position does the return vehicle ignite its engines, climb from the Martian surface, dock with an orbital transfer stage, and begin the journey back. Even that return is fraught. The outbound spacecraft no longer exists. The inbound one must be pre-sent or manufactured on Mars. A damaged ascent vehicle means the crew is stranded. A failed ISRU fuel plant could trap astronauts on a world 50 million kilometers away. Mission design must therefore layer redundancy upon redundancy. Multiple power sources, backup life support systems, spare suits, oxygenators, scrubbers. Spare parts may be 3D printed using regolith for metal feedstock. Every solution must anticipate failure and permutation. But there is beauty in the challenge. A surface stay allows scientific exploration unlike anything in human history. Astronauts can drill beneath the soil for ancient ice, search for biosignatures in clay deposits, explore lava tubes for potential habitations, and operate with real-time hands instead of delayed robot commands. They could build the infrastructure that makes Mars a foothold for future missions, not a dead-end destination. Humanity may learn to live off-world. Seeds may sprout under artificial lights. Water may drip through filters recycled from Martian ice. Solar arrays may hum in thin sunlight. For the first time, humans would exist as interplanetary beings. The long stay is not simply a waiting period, it is the foundation of settlement. When Earth and Mars align again, the crew boards the return vehicle and sails across the void once more, this time toward home. The psychological inversion on the return trip may be profound. Outbound, Earth shrinks. Inbound, it grows, not just in size, but in meaning. Familiar gravity, blue sky, fresh wind, oceans, rain. The crew arrives changed, physiologically lighter, psychologically heavier, historically immortal. That moment will conclude not a mission, but the first chapter of human expansion beyond Earth. Mission duration is not just about getting there, it's about living there long enough to return. And while these timelines frame what is possible with today's and near-term propulsion, there is one more factor shaping how soon we take these journeys at all: the organizations building rockets, habitats, engines, and plans. To reach Mars, we need dreamers, but more importantly, we need builders. The next chapter takes us into that world, the agencies and private innovators pushing humanity toward Mars. Achieving a human voyage to Mars is not the work of a single nation, a single agency, or a single billionaire's dream. It is a civilization-scale endeavor, requiring decades of science, engineering breakthroughs, will, financial commitment, and relentless human creativity. Today, four primary forces are shaping our path to Mars: government space agencies, private aerospace companies, international scientific collaborations, and a growing global community of engineers, researchers, and innovators. Their goals do not perfectly match, but their trajectories intersect, forming the scaffolding of humanity's first interplanetary future. For decades, NASA has been the backbone of Mars exploration. From Mariner flybys in the 1960s to Viking landers in the 1970s, from Spirit and Opportunity rovers to Curiosity and Perseverance, NASA has built the longest-running roadmap to Mars. Its Artemis program, designed to return humans to the Moon and build a lunar gateway station, is more than a scientific venture. It is a proving ground. NASA believes the Moon must become a test lab for Mars operations. Life support stress tests, radiation shielding experiments, ISRU fuel production, surface habitat simulations, and psychological endurance studies. If humans can live sustainably on the Moon, they can survive the harsher environment of Mars. NASA is also developing the Space Launch System, SLS, currently the most powerful operational rocket on Earth, capable of pushing heavy payloads into deep space, habitats, cargo modules, surface vehicles, and eventually crewed spacecraft bound for Mars. Alongside SLS is Orion, NASA's deep space crew capsule, built for multi-week missions with advanced radiation shielding and autonomous navigation. But even NASA acknowledges that SLS plus Orion alone are not enough for Mars. They need refueling capacity, deep space habitats, and landers capable of Mars descent, which is where collaboration becomes essential. In Europe, ESA, European Space Agency, contributes critical science, robotics, and engineering. ESA built instruments aboard NASA rovers, co-developed the ExoMars Trace gas orbiter, and is working on sample return missions, steps crucial for biological analysis and pre-human safety assessments. ESA also designs deep space life support systems, radiation models, and next-generation solar arrays. Europe is not racing to Mars alone, but rather weaving itself into a global mission framework. ESA provides stability, research depth, and engineering precision, the sustainable backbone for long-duration missions. Meanwhile, countries like Japan, JAXA, and Canada, CSA, contribute robotics, navigation technology, and scientific payloads. JAXA's work with asteroid sample return missions demonstrates navigation excellence in deep space, while CSA's robotic arm heritage, Canadarm1/2/3, will shape surface, operations, and off-world construction. India's ISRO, with the Mars Orbiter mission, Mangalyaan, proved that cost-efficient interplanetary navigation is possible, opening a future where Mars is not just a superpower domain. China's CNSA has already landed rovers on the Moon, deployed space stations, and placed spacecraft into Mars orbit with the Tianwen-1 mission. All clear signals that multiple nations intend to reach Mars within decades. But the most dramatic acceleration toward Mars has not come from governments. It has come from the private sector, especially SpaceX. Under Elon Musk's vision, SpaceX has made rapid reusability the foundation of interplanetary economics. The Falcon 9 booster lands and flies again, cutting launch costs from hundreds of millions to tens of thousands per kilogram. Falcon Heavy expands payload capacity. But the true centerpiece is Starship, the largest, most ambitious rocket with full reusability, stainless steel structure, in-orbit refueling, and methane engines specifically designed for ISRU refueling on Mars. Starship is not merely a rocket. It is a planetary logistics vehicle. If successful, it could transport 100+ tons per launch, or dozens of crew members at a time. Instead of NASA sending 2 astronauts every decade, Starship imagines hundreds of settlers each window, opening Mars not as a flag-planting mission, but as a migration pathway. SpaceX is also developing autonomous landing systems, life support hardware, radiation design studies, and Martian surface infrastructure concepts. Solar farms, ISRU plants, pressurized habitats, even stainless steel factories fueled by CO2 ice electrolysis. Yet SpaceX is not alone. Blue Origin envisions infrastructure, lunar mining, fuel depots, space manufacturing that could eventually support Mars logistics from cislunar space. Relativity Space is 3D printing rockets, reducing manufacturing complexity and enabling on-demand part fabrication, a capability that could someday extend to Mars-based printing. Rocket Lab is developing smaller but highly adaptable launch systems and deep space spacecraft. Axiom Space seeks to build the first commercial space station, a stepping stone for long-duration habitation design. Lockheed Martin, Boeing, Northrop Grumman, Airbus, Sierra Space, and hundreds of subcontractors around the world build propulsion systems, life support modules, docking ports, avionics, cryogenic storage, heat shields, communication relays, and descent engines. Mars is not one company's dream. It is the combined output of thousands of hands, tens of thousands of minds, and millions of hours of work. These groups collaborate and compete simultaneously. NASA funds private development, SpaceX contracts government payloads, ESA coordinates sample missions with NASA. China and Russia develop their own parallel paths. Startups innovate rapidly. Researchers publish breakthroughs openly. The ecosystem is chaotic, but alive. Humanity rarely progresses through linear planning. We advance through overlapping momentum, trial and error, leaps and stumbles. The race to Mars is shaping up the same way. No single actor pulling alone, but a multi-vector push from every corner of the aerospace world. And this leads us to the most profound question of all. Not how we will get there, but when. When will engines be ready? When will habitats survive? When will astronauts step onto Martian soil and look back at Earth as a distant blue dot? The technology is emerging. The players are assembling. But the timeline is still unwritten. That brings us to the next chapter. When will the first humans actually launch toward Mars? Predicting when the first humans will journey to Mars is both thrilling and precarious. It sits at the intersection of engineering capability, funding stability, international cooperation, will, and sheer human determination. Unlike the moon landings, which were fueled by Cold War urgency and national pride, Mars demands a deeper, slower commitment. It requires a mission architecture that can sustain human life for years, not days. Still, the timeline is gradually converging. While we cannot mark a calendar date with certainty, we can analyze milestones, development trends, agency roadmaps, and launch readiness to produce an informed expectation for humanity's first step onto Martian soil. NASA's roadmap places crewed Mars missions in the late 2030s to mid-2040s, assuming Artemis achieves its goals of establishing a permanent lunar presence and proving technologies crucial for deep space. Artemis is not a moon program. It is a Mars preparation program disguised as one. The Lunar Gateway Station will test long-duration habitat systems, radiation protocols, autonomous operations, and deep space EVAs. The Moon will host ISRU tests, power systems, and regolith construction, smaller-scale analogues of future Martian infrastructure. The success or failure of Artemis will directly affect Mars readiness. If Artemis runs smoothly through the early 2030s, NASA could begin human Mars hardware integration by that decade's end. If delays escalate, Mars may slip into the 2050s. SpaceX, in contrast, is dramatically more aggressive. Elon Musk has repeatedly stated his intention to send humans to Mars within the 2020s. An optimistic timeline that most aerospace analysts consider technically unrealistic, but strategically valuable. SpaceX's true target is more likely the early to mid-2030s, contingent on Starship's development, orbital refueling capability, and successful atmospheric entry tests. As of today, Starship has reached space, demonstrated full-stage stacking, and executed multiple high-altitude maneuvers. But it has not yet shown orbital refueling, long-duration life support, or controlled atmospheric re-entry at scale. Each of these is a breakthrough moment. Without orbital refueling, Starship cannot carry enough payload or propellant to reach Mars with crew safely. Without reliable EDL, entry, descent, landing, crew cannot survive arrival. If SpaceX solves these major challenges within the next 5 to 10 years, human Mars readiness by the early 2030s becomes plausible. China's CNSA offers a third trajectory. China has rapidly accelerated its space development, successfully placing orbiters, landers, and rovers on both the Moon and Mars in just over a decade. They are developing super heavy launch vehicles, Long March 9, lunar habitats, and deep space navigation centers. China has openly stated plans for a human Mars mission around 2035 to 2045, closely aligned with NASA's projected timelines. Unlike private companies, national space programs move slower but more methodically. If China commits a multi-decade funding stream and maintains stability, they could deliver a parallel mission window. And if NASA falters, China could attempt to claim the first footprint. Europe, Japan, India, and Russia are more likely to contribute to multinational missions rather than lead them, though surprises remain possible. ESA may host habitat and life support modules. JAXA may develop ISRU robotics and landing systems. ISRO may lead cost-efficient cargo deployment. Russia's future is less predictable. Once a space superpower, now inconsistent in mission execution. But Mars may ignite a new coalition, much like the ISS did decades ago. But technology readiness is only half the puzzle. The planetary alignment itself dictates when ships can depart. Launch windows ideal for crewed missions occur roughly every 26 months. But not all windows are equal. Some windows shorten transit, others lengthen it. Some stack well with return alignments. Others force extended surface stays. If we imagine technological readiness emerging around 2032 to 2036, the most favorable launch windows become 2033. Early possibility, extremely ambitious. Requires accelerated propulsion, crew systems, and refuel demonstration. 2035. More realistic if Starship or NASA deep space vehicles mature fast. Still cutting edge and high risk. 2037 to 2039. Strong candidates for NASA-led or multinational crewed missions. Mars and Earth in more favorable distance profiles. 2041 to 2045. Most likely window. If delays occur or testing demands longer safety margins. Aligns with NASA, CNSA, and ESA projections. Beyond 2045, Mars missions shift from first attempt to delayed arrival. The world will expect progress. Private space will grow impatient. International pressure will mount. Breakthrough propulsion, NTP, NEP plasma drives might mature by then, enabling faster timelines. A bold yet plausible prediction emerges. First uncrewed full-scale Mars landing systems, early 2030s. First crewed orbital Mars mission, 2033 to 2037. First human landing on Mars, 2037 to 2045. This range allows for engineering setbacks, funding hurdles, regulatory evolution, and necessary perfection of life support and re-entry hardware. If private innovation accelerates and international cooperation strengthens, humans could step onto Mars in the 2035 to 2040 bracket. If propulsion or habitat systems delay, 2045 becomes the safer bet. In either case, the reality is this: the first person who will walk on Mars is likely already alive today. Somewhere on Earth, in a classroom, a lab, an engineering company, or maybe even training as a pilot, the future Martian astronaut exists. They may be American, Chinese, Indian, European, Brazilian, African, or an unexpected voice from a nation new to spaceflight. They may be a scientist, an engineer, a doctor, a botanist, or a multidisciplinary explorer. They may step onto Mars with a robotic lander's shadow at their feet, with billions watching through a delay, with 410 million kilometers of silence behind them. And when that moment comes, the first footsteps in red dust, the world will divide into before and after. Before Mars, humanity was planetary. After Mars, we are interplanetary. But to answer our original question, how long will it take to get there? We must now conclude the journey. The final chapter brings every piece together: propulsion limits, planetary alignment, human endurance, travel speed, mission duration, and future breakthroughs. We close by summarizing the most realistic travel time with today's technology and how tomorrow may reshape it entirely. The question that began our journey now returns: how long would it actually take us to reach Mars? After traveling through orbital mechanics, propulsion, human biology, mission constraints, and emerging technology, we can finally answer with clarity and with wonder. Using today's technology, following the same orbital transfer paths our robotic explorers have taken for decades, a human mission to Mars would require approximately 6 to 9 months of travel one way. This is not a guess, not an approximation spun from imagination. It is a number forged by real spacecraft, real physics, and real missions across half a century. Launch during a favorable window, accelerate into a Hohmann transfer orbit, coast across interplanetary space at tens of thousands of kilometers per hour, and arrive months later at the red world, shining like an ember in the void. Yet this journey, even at its quickest within current capabilities, is only the beginning. Astronauts will likely spend more than 500 days on the Martian surface before planetary alignment returns for the voyage home, followed by another 6 to 9 months back to Earth. A full mission stretches across 2.5 to 3 years, testing endurance, resilience, technology, and the very definition of human adventure. But propulsion is evolving. Nuclear thermal engines may compress travel to 3 to 4 months, nuclear electric systems to 2 to 3 months, and advanced plasma drives could deliver transit windows approaching 6 to 8 weeks. Push further into theoretical propulsion, and fusion engines may cut that time to 30 days, antimatter engines to days, and exotic space-time manipulation someday to mere hours. The journey from Earth to Mars could shrink from seasons to commutes, as revolutionary as the shift from wooden sailing vessels to jet aircraft. Still, the first crewed missions will not wait for perfection. They will fly with risks managed, not erased, with technology refined, not transcended, with timelines measured in months, not miracles. And when that spacecraft, whichever nation, whichever company, whichever crew, fires its engines for the final insertion burn, humanity will cross a threshold no species before us has ever breached. We will leave not just our world, but our cradle. We will touch another planet and know, in that moment, that Earth is not the boundary of our existence, only the beginning. So how long does it take to go to Mars? With what we have today, 6 to 9 months. With what we are building, 3 to 4 months. With what we may someday achieve, weeks, days, perhaps less. The answer is both humble and breathtaking. We stand on the cusp of interplanetary history with the tools to begin and the imagination to continue. The first human to walk on Martian soil may already be alive, dreaming, preparing, somewhere under our sky. The journey will be long, the risks will be real, but the reward will redefine what it means to be human. This concludes our exploration, yet it also opens the door to everything that comes next. One planet behind us, one planet ahead, and a journey measured not only in months, but in courage. The next step is ours. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.